Just okay. Can you hear me now? Okay. So, in today's class, we are going to discuss the solvent contribution. As I told you in previous classes, that there are three types of contributions which can affect the actual magnetic field that is experienced by the concerned nucleus. So we had local, neighboring effect, neighboring group effect, and then the solvent. This is the third one in that series. So, solvent molecule, if it is magnetically active, uh, it is it will affect the overall NMR spectrum that you will get. It is something like if you have something which is polar and can form hydrogen bond, if solvent is like that, then there's significant broadening. Usually you will find that broadening is observed, and also you will see a slight uh, chemical shift moves to higher values. So these are few things that we will observe for protons, uh, chemical shift values. So few examples we will see, and yeah, so it is because of these reasons, because hydrogen bond is dynamic. It keeps what we mean by saying dynamic is that it is in the process of forming, breaking at the same time. Some of the bonds are being formed, some of the hydrogen bonds will be broken in a solvent. So because of that, there is a wide range of T shielding, and in turn you will have wide range of these chemical shift values uh, spreading around a particular uh, chemical shift. You will find it is so overall effect is that there is a width of the peak increases. Width of the peak, as I told you in the last class, it is measured in terms of FWHM, full width at half maximum. And so concentration, so if there is this hydrogen bonding is there, then it is yeah, difficult to predict, because temperature, acidity, or anything basicity, if of the solvent can have multiple effects on these things, on this, and it tends to be broader for all of these reasons. Difficult to predict, and one thing is that you will always find it broad. uh, mhm. So usually when you are doing with protons, NMR spectra, especially that contains protons, you would like to take a solvent which does not usually interacts with the system. So, choice of this solvent is very important. Otherwise, the broadening unnecessarily sometimes complicates the thing. So what you see is a simple example over here, which is the case of OH proton, this one, and this particular thing is appearing at slightly uh, it is expected to appear at a higher chemical shift value. But besides that, because of hydrogen bonding interaction, intermolecular hydrogen bonding interactions would be there, and the peak is broadened. If you see carefully, then if you zoom in, so So if you try to zoom in over here, so this is the peak that you see. So as I told you, full width at half maximum, if you calculate, that is gives you the idea of width. So width here is half width would be, full width at half maximum would be somewhere here. So you see, at half width it is having substantial as compared to other peaks. This is maximum, and half of this will be very less compared to the full width at half maximum for this. That's why we say that the signal is appearing broad. It is less intense because H is only one of its own kind, whereas other protons are numerous, more in numbers. So that's why it appears in less intense, but the width of the peak is much larger as compared to the HB or any other protons. So you look in terms of full width at half maximum and then try to see. So in all these species, wherever hydrogen bonding is possible, you will find it there is increased de-shielding, and also so moving to the higher ppm values, this is a common thing which is observed due to de-shielding. So hydrogen bonding is so this is slightly difficult to imagine, because hydrogen bonding, what happens in hydrogen bonding is that the proton that you are taking pictures, so for example hydroxyl proton, the OH, imagine OH, so this is with a partial positive charge that we can imagine. So yes, huh? Oh, it, okay. So hydrogen bonding, generally you will find that it causes, for the hydrogen bonded protons, the NMR signal will move to higher ppm or values due to de-shielding. So this is something slightly difficult to imagine, because when we are talking about hydrogen bonding, you can think of this hydrogen, that is, for example, if you have something like, and this will have interaction with the the this proton, right? So this is how we see the hydrogen bonding interaction. It is a lone pair that participates. So lone pair of the other molecule, which is in which you have hydrogen bonded to a highly electronegative atom such as this. So it is, but because in hydrogen bonding interaction, actually we are seeing, suppose it is an isolated condition, it is having a positive charge, that which means that electron density has been removed from its vicinity. The proton, this is your proton of concern, and then this solvent molecule comes in, and interaction happens with this lone pair of electron. So actually it is receiving this electron density. That is the kind of view it is. There is a donor atom which is giving you the electron density, and so a simple point of view that you can think that it should have pos क्या, hello, फिर कट रहा है क्या? हेलो? या आवाज कट रही है क्या? हाँ, आवाज आ रही है कि नहीं? हेलो? सिग्नल बीच में कट जा रहा है। ओह नो। हम्म। सो मैं I hope so. Receiving this electron density, so this is the view that we have. Proton is interacting with the lone pair, so in the because of the presence of such a solvent molecule which can form hydrogen bonds, actually this lone pair is coming closer, and you are having this interaction. So it is receiving the electron density. That is the view, and because of this electron density from the other atom neighboring solvent molecule, we can it is easy to imagine that it should be shielded, but we are talking about de-shielding when hydrogen bonding occurs. So this is if you so it is so actually we are not thinking in the terms that we should have concern about the not actually the electron density that is coming from, but the field that is set up by the presence of that electron. This is what we have learned in previous class also, that it is not the so magnetic field is can be different, can have different effect at different points. Huh? Yeah. Okay, so the important thing was that de-shielding जो हो रहा है वो we have to think of in this term, the field that is set up due to the electron, not actual the electron density which is coming closer to it. So इलेक्ट्रॉन से इंटरेक्शन ना सोच के हम इलेक्ट्रॉन जो मैग्नेटिक फील्ड सेटअप करेगा उससे इंटरेक्शन के टर्म्स में हमें सोचना होगा। ठीक है, ये ज़्यादा इम्पोर्टेंट है। So not the electron density but the magnetic field that is set up and the effect that it will have. So usually if you what we find that the field setup is the whenever hydrogen bonding occurs, you have the interaction with the neighboring lone pair of the other atom, other molecule, a solvent molecule, will actually cause de-shielding. That is, it will experience overall greater magnetic field uh, as compared to the reference, and so it will come into resonance at a lower value of applied magnetic field. So it is in this context that we talk about de-shielding of due to hydrogen bonding. Uh, so there is a change. It will also cause a change in the chemical shift value, and this chemical shift change in the chemical shift value is evident when you have intermolecular hydrogen bonding. Then this thing the hydrogen bonding interaction is a variable. It keeps varying if it is intermolecular in nature, but if it is intramolecular then it is not affected by the solvent, and so you will observe although there will be hydrogen bonding interaction, the extent of hydrogen bonding is not affected by the solvent, so it remains intact, unchanged in such cases. So for example you can see over here, you can see that thing happening. For this is the methanol in okay, so methanol this is the pure methanol, and you find this is what happens. So this is so in a pure methanol you have so many methanol molecules, each one of them having hydrogen bonding interaction. So you can see that in case of pure methanol, 100% in the pure solvent, you are having this at higher value. The hydroxyl proton appears at a higher value, whereas if you add a solvent, if you make a dissolve methanol in a solvent which cannot make any hydrogen bond, such as say CCl4, then you will find that it is in absence of hydrogen bonding interaction, it shifts to lower values. And so this is so in case of pure methanol, you are having intermolecular hydrogen bonding, and because of that, when you change the solvent and make a solvent which does not makes any hydrogen cannot make any hydrogen bond, the example is CCl4. So in that case, there is the isolated hydroxyl proton, and then you can imagine it is not able to interact with any other that hydrogen hydroxyl moieties, and so it is appearing here at a lower value of relatively lower value of the uh, chemical shift. Okay, so this kind of distinction in NMR spectrum will be obtained only if you have intermolecular hydrogen bonding. Intermolecular hydrogen bonding, um, and which can be affected because this is the intermolecular hydrogen bonding which can be broken up by a foreign molecule which can like when you change the solvent. So similar things like happen, and so no hydrogen bonding is observed when for solution of methanol, when CH3OH is dissolved in CCl4. So this is what we are observing in the second panel, left hand side, second panel, lower panel, I mean from top to bottom. If you are viewing in this segment, this is what is happening. Pure methanol, one methanol molecule surrounded by several methanol molecules, each one of them can make hydrogen bonds with each other. So this is intermolecular hydrogen bonding, and when you put that, say make 5% solution of CH3OH in chloroform, tetrachloromethane, or CCl4. CCl4 is your solvent. Now this is your solvent, then it cannot form hydrogen bonding interaction. A dilute solution, this solution is a dilute one, so that it is each of the molecule are well separated, each of the methanol molecule are well separated, and you cannot expect any hydrogen bonding to occur, and in such situation this is what you observe. In contrast, there is another example of this particular molecule. This is C double. So you can see you have two type of hydrogen protons. One is the hydroxyl proton here, and another one is CH, this proton. So you can see that in this particular case there is a possibility of intramolecular hydrogen bonding. So if I can show with dotted lines, this is the intramolecular hydrogen bonding can happen here. Intramolecular hydrogen bonding happens here. So this particular thing, this particular proton, the hydroxyl proton, if you see, uh, it will be affected, but it will be affected to the same extent irrespective of what the solvent is. So intramolecular hydrogen bonding in pure compound, this acetyl estimate, so in pure compound, and then dilute solution in the same way, solution in CCl4, where no hydrogen solvent cannot solvent is not affecting the hydrogen. So isolated view, when the molecules are separated, well separated, dilute solution, the solvent is cannot form hydrogen bonds. So still, so what you see here, it remains unaffected, no change, no change in the, because it is the intramolecular. So this hydrogen bonding interaction is not affected by change of solvent, because it is a inherent structure of the molecule. It is inherent to the structure of the molecule, and one end of the this carboxyl end, sorry, the carbonyl end interacts with the hydroxyl H uh, proton, and you have a thing, and this will remain as it is. This interaction is not affected by whatever, doesn't matter if you change the solvent to CCl4, isolate the molecules, it is still like that. Or if you have a pure compound, in that case also it will be still appear to be same. So the position of this OH hydroxyl proton in this particular case remains unchanged. So we that was the point I was trying to make earlier, that it is only the intermolecular hydrogen bonding which is affected in NMR. Intramolecular hydrogen bonding remains unaffected with the change of solvent. So this is the solvent, uh, yeah, the distinction can be made only if it is intermolecular hydrogen bonding. And this was what previous slide I was trying to make a point. So a change in chemical shift will be obtained if it is intermolecular hydrogen bonding. Intramolecular thing remains unchanged, whatever you may try with concentration or change of solvent, it will remain unaffected. So that was the thing, and we obtained this kind of, okay. So we saw it happening in methanol. This was the case of methanol interacting with methanol, and methanol not able to interact with other thing. So this is what we found, that something like this happens. Yeah, so you have methanol interacting with methanol in pure compound, this panel, and the bottom panel happened like that. So okay, so this was the kind of thing. So this is a pure, uh, so the top panel were both were in pure forms, and pure form, and this was dilute solution for both the compounds in CCl4, where you saw one changes. So the change you saw here, in this case there was no change. So this is the thing that is point to be noted: intermolecular versus intramolecular hydrogen bonding, and how the NMR spectrum is affected with change of solvent. Okay. uh, yeah, so this is the point I already stated, this point, that you dissolve it, so it tetrachloromethane, it breaks down the hydrogen bonding, no hydrogen bonding interaction between the molecules. and this happens. Okay, similar thing can so it is also very helpful in biology. In biological systems, this base pairing that presents interaction of the nucleic acids, nucleosides with each other, that can be detected by NMR, and it is a great help in elucidating the structures of explaining the structure of such a large biomolecule, which is very very complicated. So here, this is the typical view of cytosine interacting with guanine, which the base pairing model that you have already studied in double helix of DNA. And this blue colored lines, this indicate the hydrogen bonding interaction. So if you look at the NMR spectrum of individually, the guanine, cytosine, individual parts, and then you mix them together, you see a very important pattern that emerges. So this is guanosine, separate, uh, isolated, so separately. Pure guanosine is having this kind of spectrum. Then you can think pure cytosine. You have, this is the spectrum. So pure, and you can see this. So if you add them together, so guanosine plus, so both are being added. So this and this both are being added together, and this is the middle spectrum that you get. So what you see, as I told you, whenever two molecules interact, hydrogen bonding occur, you can expect the peaks to be shifted to higher value, higher ppm values. So that's happening. You can see here this shifting to here, and this one too. So it shifts and it also becomes broader, and that's why you see that the two peaks which were appearing here, they have moved to a higher overall value of the chemical shift, and it has become, because of the broadening, they appear to be merged into one. So this kind of thing happens, and it is very helpful that it tells you that there is interaction happening. The guanine and cytosine are so located in such a way that they can interact, and hydrogen bond has been formed in the thing. If they are separated enough in the structure, they can't form the hydrogen bonds. So it is very helpful, quite helpful. Uh, this is in biochemistry, explaining this kind of structures, change in shift, change in the proton, NMR, proton, this hydroxyl protons, or not hydroxyl proton, I am talking about this NH protons rather, uh, base protons. So these are showing shifts from the to the shift towards higher ppm values in the mixture when the two guanosine and cytosine are mixed, and also a bit of broadening is seen in each one of them. So full width at half maximum, that is the increasing. So it this NMR thing is yeah, whenever hydrogen bonding occurs, it is in many cases it also becomes inconvenient because of hydrogen bonding, because the shift is not, you cannot predict how much it will shift because of hydrogen bonding, depending on amount of water present, or the solvent which can do this kind of hydrogen bonding. You can have variable shift in the spectrum. So usually you want to have a dry solvent for NMR, and how dry it is, that will affect your signal, the shift in the signal. So it is of interest in biochemistry, as I told you, in determining this structure, the interaction between two types of such nucleic acids in the DNA base pairing model also. Uh, yeah, so components that are interacting, C pairs with G. This is what we know, and it is through the hydrogen bonding interaction that is seen. And so when you mix them together, you see a clear shift. So you see this part, this is unchanged, this is unchanged. You add the two together, you will get this one on the left and right. If you see the mixture left at the left end and the right end, it is remaining unaffected. You sum it up, simple summation, and it is appearing like that. But the middle portion is greatly affected, where you see a clear shift from both the spectra taken together. So cytosine, and from the point of view of cytosine spectrum, there is a shift. There is a shift to this side. From this point also, there is a shift towards higher ppm side. So this is something that gives a clear indication that the two things, the nucleic acid, are interacting, having hydrogen bond interaction. Similarly, the solvent, if it is having a ring current, such as if you suppose your solvent is benzene, it will be it is aromatic, and it will have a intense local field that you can imagine. And so this is the magnetic lines of forces. So this is your solute, and this benzene ring is the solvent. So in this particular case also, you can think that uh, depending on the placement of the solute molecule, you can have different type of interaction. If it comes in the plane of the ring, in the molecular plane of benzene, then it will be de-shielded over here. If solute comes here, if the solute is here with hydrogen, it will be de-shielded. But if the solute is present over here as shown in the picture, the H, it will be shielded. It will, the applied field is in this direction, and it is opposing it over here if it is above the plane of the ring. So this kind of things do happen. So this is another example. This is so this was an example where you have pi electron cloud, aromatic structure is there in the solvent, and that can also affect NMR signal, and it will be very unpredictable because placement of the solute molecule, uh, if it is randomly moving, it may sometimes be come in the plane of this. Solute may come in the molecular plane of the benzene. At that time it will be de-shielded, and if it is here, it is shielded, and so you have net magnetic field is reduced. You can see the arrows pointing in where they are pointing. So that is something that gives you a very unpredictable kind of NMR signal, unpredictable shift, you can say. So one time it is can give rise to local currents, shield or de-shield, both can happen for the solute. At least in hydrogen bond, you were sure that it will be de-shielding that will come out whenever hydrogen bonding interaction. So if you have solvent like water and something, you can expect that kind of thing. But if you have benzene as the solvent, because of this aromatic ring, uh, pi electron cloud, you have a different kind of interaction which is even more unpredictable, because both shielding and de-shielding can happen. And so so this can be a very tricky thing. Okay, so now we are so we started the discussion with example of methanol NMR spectrum of the methanol. And now, after discussing different points, we are coming back to it because one of the aspect was not yet explained, that is the splitting pattern, the splitting multiple set that you are observing. So you can see triplet 3 peaks appearing over here. Here you are seeing a quartet, and this is singlet. So methyl, methylene protons, and then hydroxyl proton. They appear at 3 different values of chemical shift, and they also appear at a there is a clear splitting pattern that we can see. Okay, so how this splitting occurs, we focus our attention on that, why this happens. And so basically it arises because that you have two nuclei at two different locations. uh, there is a coupling between this, so there's each magnetic nucleus can contribute to the local field and then there is a modification in the resonance frequencies in a very complex way. And so we are going to understand this part. So just like we have earlier talked about coupling of orbital and spin quantum number for case of electrons, here also we can think of coupling of these two things, coupling of one this angular momentum of one nucleus with the other. Okay, so then we define this coupling constant at J, and it is the units are hertz. It is its units. So the interaction energy is of the two spins is given by this I1 and I2 are the two angular momenta. So I1, I2 angular momenta of the two interacting momenta is plural of momentum, so you should know that. So the two momenta of two different nucleus so if they have different magnetic moment and different angular momentum, different, so they can add up in different fashions. So we have, if you remember that LS coupling scheme, you remember we had different orientation for the same value of angular momentum. You can have different orientation for, and they were combining with each other in different ways. Vector addition can happen. So in a similar fashion we can think of the interactions here, but it is the two interacting spins, two different at two different locations. So that interaction gives rise to this kind of uh, thing, splitting pattern. And this interaction energy is proportional to I1 dot I2, the dot product. So that's why we call it scalar coupling constant, because it is the dot product that defines their energy. And this, when you remove this proportionality constant, this is the constant that will come, Hj by H cross square. Okay, and this this particular constant J, the spin coupling constant, is independent of the applied field, and uh, because they are unaffected. They have okay, so each line will be split into so if you have if you can count such things, that how many such nuclei are there, so there will be a splitting that you will find is happen. And if one is split by a certain amount, the other will also be split by the same amount. To the same extent, the splitting will occur for the other nucleus. So if first nucleus is its signal is split into two, the second nucleus will also likely to be split into two because of the mutual interaction. So mhm, hmm. So usually when we are talking about in NMR, when we talk about this coupling of the two nuclear spins at two different uh, end of the spectrum, two different so we usually use this alphabetical pattern is used. So suppose two interacting nuclei are having very different chemical shift values. That means just as A and X, if they have a very different, we use the term A and X because the letter A and X are well separated in the alphabet. And so if there are two nuclei which are having very different chemical shifts values, we represent the term, we use the term A and X in that context. And if the two interacting nuclei are closer to each other in this chemical, in terms of chemical shift, it is not a, when I say close or far, it is not a Cartesian coordinates that I am talking about. I am talking about the distance, not the it is the chemical shift values that I am talking about. In terms of chemical shift, they how far they are separated on the spectrum. So the two interacting species, if they are far apart in terms of chemical shift values, we label them as A and X. If they are close together, A and B, just like two letters A and B are close in alphabet. So in terms of chemical shift, we also talk about coupling. When we describe coupling, we talk in these terms. So AX system or AB system type system. So so we have the protons, two proton in two different environment, one having higher chemical shift, one another having low value of chemical shift. So that system will be described as AX system. So this doesn't mean that they are uh, in a 3D coordinates, XYZ coordinates, they are far apart. They may be very close to each other, next door neighbor, they can be next door in 3D coordinates. But in terms of so for example, methyl alcohol CH3OH, so the two set of protons, the methyl proton and hydroxyl proton, are in a three-dimensional space. They are close to each other, but in terms of their say in terms of their chemical shift values, they may be far apart. So that's how we have to think in for these things, these interactions. So so suppose, so we are talking about half spin nuclei, like proton is a half spin. So if we stick to that system, uh, so A and X, there are two nuclei A and X that very different chemical shift values. Then we can also, because their chemical shift values are different, very much different, their frequencies are also very different. Uh, so we first consider this system. So we already know that for single spinning nucleus, this is how the splitting occurs. And so you see this we are familiar with this particular thing. No, not, so there's few things which is going below the screen. Just a moment. Yeah, so this is already we are familiar with. Yeah, this is the picture that we already know about for single one, single nucleus. If you have one nucleus, then you can think of one which is ms, so plus half and minus half. So this is the, in presence of magnetic field, this was the separate energy levels split into two, like this. Now if, when we are talking about two such nuclei which are magnetically active, have a half spin ms, then what will happen? We can think of four such things. So we can have force combinations are possible for considering the spin at A, spin at X. So alpha alpha means both are having plus half, as the quantum numbers are plus half. Whereas, so you can expect the orientation to be upspin. Alpha beta combination represent where something you have this alpha beta combination is something that you can, yeah, alpha beta means alpha a beta x. So this is something that we talk in sense of, so a atom can have alpha or it can also have beta. So alpha means plus half, beta means minus half. Similar thing can happen with x. So these are two probability, so plus half or minus half, and then you can work out the permutation combination. So there's first combination which is alpha alpha for both a and x. Then at the other extreme you can have beta beta for both. This is the other extreme, when both the spins are minus half for a as well as for x, and in between these two extremes you have two more combinations. So when one of them is alpha, another one is beta. So alpha a beta x, beta a alpha x. So these are four different possibilities that we can have, think of. And now we can draw this, accordingly we can draw the energy level diagram for both the things. And this will be something like this. So in case of no spin-spin coupling occurs, if there is no spin coupling occurring, then we can have alpha a alpha x, alpha a beta x. So these are the four energy levels that we can think of. But what happens is that if there is spin-spin coupling, if the two systems are interacting, the A and X, the two nuclei are having interactions, then the situation changes. You have what we are seeing here, both the system where both have plus half ms. So this is plus half, this is also plus half, this is what we are seeing. And in the, when beta beta, we are talking about both having minus half ms spin values, or rather we write mi for nucleus, no, so we can subscript mi. So both are having minus half. So this is the situation at the extreme. So this is the thing that we have in absence of spin coupling. Only four states with this energy is can be expected. So these are the energy levels that can be formulated: minus half h mu x, and this mu is the Larmor precessional frequency, that we have for the system at A and X. So what happens if the two spins at for the A and X are same type? In both cases you have a increase in the, if the spin coupling occurs, there is increase in the energy for both the things by a certain amount, which is given by 1 by 4 h into j. And if the spins are different, alpha beta or beta alpha, then both are showing a decrease. You can see in both cases there is a decrease by 1 by 4 hj amount. So net result is that you can think of four transitions that can happen now, and you can see the first transition, the first arrow, it is so alpha. So you have alpha A, alpha X here, and the situation here, it is going from alpha A to beta X. So there is only change in the spin of the beta positions when the energy is absorbed. So for the X, A remains same. First transition is that. The second arrow that you are seeing, you have there is only change in the spin of A position. Spin of the A is changing, X remains same. Okay, so this is how we interpret during one transition that is shown by this arrow. Each one of these transition, only one of the spins is changing. Okay, and it is one spin at a time. So this is a four transition that is possible. And look at very carefully, if you look at this for change in A. So alpha A to beta A, so this will be the change in the A. So this particular thing is here. Let's see this. This is one. Then the same alpha A beta A here. You can see this is another one. The difference between the two is this one. What is the difference between the two arrows? Equivalent of this. Okay. So at the position of A, when in absence of X, A would have appeared as a single peak. Now the same transition alpha A to beta A is now appearing at two different positions, slightly separated from each other by this particular. So the separation between the two is about, we will see this, yeah. So similarly, if you are looking at the X values, alpha X and beta X, you will find that they are also separated by the same. So look at the transitions here, X and alpha X beta X. This is another alpha X beta X, alpha X to beta X, alpha X to beta X. So this is the change at the X position, alpha to beta. And in both these cases, so again the difference between the two arrows is this much. Okay, so now you can see that how it is coming out. We will try to, so we can have transitions either alpha to beta of A or X at one point of time. Other nucleus remains unchanged during the transitions. So actually, so spin-spin coupling is usually much smaller than what you see. So much smaller. So splitting that you see due to spin-spin coupling is much smaller. Only to this has been exaggerated here to show that the difference is. You can clearly see that pictures you can draw and show it very well. Only for that purpose it has been slightly bigger, slightly greater separation has been shown. In actuality, it is always, in reality, it is always less than the less splitting is caused by this J, and there's greater splitting due to the B naught, that magnetic field. So if you look at this, if you want to calculate the energy for each one of them, so we have already seen in previous classes what taking into account the so this MA is the plus half or minus half thing that we were talking about. The Z component, the for the nucleus, that Z component of the nuclear spin momentum is given by this factor, at A position for the nucleus A and nucleus X. So this is can be plus half, oh sorry, what I am writing, plus half or minus half. Similarly this mx. So this is the same thing that we have already for one nucleus. We have written this equation considering the shielding constant. This is the shielding constant, remember. And so two different nuclei will have two different energies corresponding to that, and so we can write as okay, this is the interaction energy for the two system, and we can simplify it further that this particular thing, this whole term was your Larmor frequency, so you can put it in terms of energy, h mu. So both of them written over here as this form. So this whole term is shortened to this. So this is the energy of interaction, mu, where the mu is the Larmor frequencies. These are the Larmor frequencies that we are talking about for A and for X, and this is what we saw. This is what we were seeing in the previous slide, the energy levels. So now if you substitute MA as plus half minus half, so if it is MA is plus half, MX is also plus half, what will be the value? Both, in this case it will be simply E will be equal to minus half h mu A minus half h mu X. So this is what you, in the previous slide, this is what we found, that, so see how this originated initially. So in case of there is no spin coupling, this would have been the energy, and now when we are including the term for when we think of both are interacting system, then due to the spin coupling there will be a term which will incorporate the product MAMX. So if you incorporate it, this is the term that you will get, indicating the spin coupling. So HJ, so this is the term that indicates, this is an additional term coming in to picture when you have spin coupling. So this so energy is affected due to spin coupling by this much amount, Hj Ma into Mx. So now if J is having a positive value, if J is positive, so coupling constant is positive, then you put the values, you have MAMX will be negative for the first part, which is negative in that case. For J positive, and higher energy is obtained, so you apply this principle, you will find that higher energy obtained if both spins are alpha or both are beta, and so if J is negative, then it will be different. So this is what we obtain when we put this formula. So you can just simply go on substituting MX values plus half. So if both have, so think of situation where you have if suppose MA is plus half, and this is also plus half values. Think of first situation, this is also plus half, then it will be 1/4. So this multiplication term will be 1/4, and that will be added up. If you have both are minus half, suppose this is also minus half, this is also minus half, so again it will be plus 1 by 4. So in both cases, when either you have alpha a alpha x, or beta a or beta x, in both situations when you multiply beta ma mx values, you will have increase by plus 1 by 4. So plus 1 by 4 term is coming over here, plus 1 by 4 term is coming over here, because of that reason. In all other cases, when either any one of them is plus half and minus half, the combination gives you minus 1 by 4, and that's why these two are appearing as reduction of the values. So simple consideration of putting the values, you can realize that how the energy increases by 1 by 4 j if beta beta or alpha alpha state is there, alpha alpha and beta beta situations both increase by 1 by 4 hj, and when alpha beta or beta alpha situation is there, it will decrease by same amount. So this is the picture that has been shown already. Another alternate view of the same is here, alpha a alpha a alpha x. So you can think of the transition one at a time. So alpha a beta x, you are having change of the alpha to beta x, and in this case, in the other case, you can have alpha a changing to beta a. So this is the transition that you are seeing, and then beta to beta a beta x, you can think so one at a time, and you are having such 4 lines that you can see. So in absence of any of them, if there were two non-interactive system, you would have got 2 peaks, but now you will find 4 peaks. And because the splitting is much less as compared splitting due to spin-spin coupling is less, so the separation will be very small, and they will almost they will be very close to each other, separated by j values. So so resonance of a system, so the change that you will find will be plus 1 minus half to plus half, something like that if it happens, and for the other system at that same time will be 0. So this is the situation that I already discussed in the previous one. So if I am talking about at a resonance at a, so you will have this, you will also have this, which is of bigger arrow indicating, and this one a little bit smaller situation. So there will be a separation between the two, and it will, so energy difference, if you calculate from the previous situation, I have already defined the energies of each one of them by in previous slide. Sorry, yeah, this is the energy of each of the states. So difference of energy between two states you can easily calculate, and when you calculate this energy, it is for the change of a. So a can change, it can be plus half or minus half h mu a. Change in del E would come out to be, so individually each of the state was changing by plus half 1 by 4j 1 by 4j hj, and the two lines that difference in energies, that is the transition lines, the signal, they will differ by plus half. One will be located at plus half h mu a plus half, and another one, so you have two signals which are, so now you can have two signals, one at h mu a plus half j half hj, and h mu a minus half hj. So the difference between the two lines would be equal to hj, right? So this is what we expect in terms of j. The separation would appear on a scale. So this is the idea that is being conveyed. If you are looking at the A resonance, the two lines will be separated by j. If you are looking at X resonance, which is appearing at a very different X chemical shift values, the two lines will be separated by this j. So this is what we you can say that in such you are having. So instead, in case of spin coupling occurs, you would observe a doublet for a doublet for a doublet for X. So chemical shift values. So this is the idea that we will further develop when we have more number of A and X together uh, appearing together. So what will happen in that case? So I think we can do this. We will follow this up in the next class when we have a large number of such some more such interacting system is there. What will happen? So all these things. So at least this idea is clearer. So that separation when A and X, there are two nuclei, both are interacting. A and X are well separated in terms of individual chemical shift values. Now if they interact, the two, and due to the spin-spin coupling, each one of them will be appearing as doublet, and each one of the two lines in the doublet at for A will be separated by j, and the same thing will be also true for that the separation between the line for X is also j. So this we will continue further in the next class.